latest and greatest episode of adventure and discovery and the Metaphysical Corner as we continue in this book, Molecular Consciousness. I am also, first of all, I have to apologize for not doing a video last week. We had, the household was waylaid by the flu. Oh, sorry about that. The household was waylaid by the flu. I wasn't, thankfully, but basically had to take care of everyone else, and everything just kind of got put by the wayside, if you will. So I just want to continue now. I have to tell you, it's been 2 weeks since I made a video, and my discovery is, if you will, of this is a never-ending process. I'm learning more and more. I'm reading several real interesting books. This, and I hope this book that we're going through, this molecular consciousness, doesn't bore you, so to speak. It shouldn't, because for example, the chapter we're going to be covering today is called the Magical Power of Chemical Bonds. And you may think, what's that got to do with metaphysics? The answer is everything. Because number one, it's all you are. It's all the universe is. Chemical bonds are everything. It's the I Ching. It's the, it's how the universe is made. So it's vitally important. It will help you understand what we're kind of doing here. How can I explain it? We're doing the basics. We're doing the arithmetic before we can do algebra, before we could do calculus. Okay, not that we're going to be doing geometry or algebra or calculus, not quite. But it's rather a primer. If you don't understand, or if you don't have any idea what is covered, the ones I've already done and the ones we're going to cover, it's not going to make as much sense as it could or should. And so it's to give you an understanding of how truly magical it all is, as far as reality, consciousness, and that type of thing. I had an interesting discussion with someone about dreaming. We'll get into that later, not today, but there's so much involved. I've had some really interesting discussions with people lately about this whole realm. And it amazes me, how complex, how much it is. There was actually, and I have it somewhere in my house. And if you're ever looking to watch something that will really open your eyes, and I gotta find it. I know I have it. It's a movie. It's not a documentary. It's like, it is, but it isn't. It's kind of a weird thing. It's about an hour and a half long, and it's called "What the Bleep Do We Know?" And I'm sure you could research it on Google, order it from Amazon or some other place. It's been years since I watched it, but it is truly fascinating. I highly recommend it. It's called "What the Bleep Do We Know?" And the answer is not much. For all we know, for all we are learning, it's one of those deals, and maybe that's the way it should be. When you discover something, you finally get one question answered, 10 more pop up. And maybe and what I'm saying is, maybe that's the way it should be. If you reach the end and it's just a cul-de-sac, well, that's not very exciting. There's so much more to all of this. And must be someone walking by the house. So anyway, let's get started with this chapter called the Magical Power of Chemical Bonds. Once again, which is something that holds us all together. It says, we talked previously about the elements, and of course the elements are defined by how many protons are in the nucleus, okay? All matter is, no one else, there's no one else on our planet other than the elements. All matter is made up of elements, and a great majority of them are social beings. That is, one finds them bound to another, one element to another. The links between the atoms are known as chemical bonds. And in every chemical bond, there is energy. It's what holds that bond together. In general, atoms are found together in groups of 2 or more. This is true for all but 6 elements. These 6 elements don't like company. They bind with great difficulty, are almost always found alone. They're called the noble gases. And they're helium, neon, argon, krypton, xenon, and radon. And there's a reason for this. What it is an atom likes its outer shell completely filled. And when it's not, you will either lose electrons or gain electrons to make that happen. Well, those elements I just listed already have them. Their outer shells are full. It doesn't want to give any up. It doesn't want any more. So they become very chemically inactive. And they participate in almost no chemical reactions. The atoms of all the elements are found in nature bound together. Atoms bond either to atoms of their kind, as many with gases we know, oxygen, nitrogen, helium. They're all, I take it back, oxygen, nitrogen, and hydrogen. They're H2O2, N2. There's 2 atoms, in an oxygen molecule. In pure nature, you'll almost never see an oxygen atom by itself. It's always bound to another oxygen atom or another element. Same thing with hydrogen. Hydrogen is H2, is 2 hydrogen atoms bound together. These chemical bonds glue atoms together. There are several modes of bonding, but the result is the attraction of the electrons of one atom to the nucleus of another. The attraction of an electron to a nucleus other than of its actual atom forces both atoms to come closer. That becomes electrostatic attraction, plus and minus. To get an idea of how close they are, in helium, it's a noble gas. The distance between 2 helium atoms at room temperature is 100,000 times the distance between 2 oxygen atoms. So in other words, helium atoms are much more boundly together and bonded, more so than oxygen. In fact, chemical bonds are the fruit of the electromagnetic force. This force pushes negatively charged electrons towards positively charged protons. Atoms are held together by chemical bonds form combinations called molecules. Matter is made up of molecules, pure and simple. End of sentence. If all the molecules of a piece of matter are identical, it's a pure compound. Water. Pure water, not like distilled. It's got no minerals in it. Is a pure compound. It's only composed of water molecules. In a water molecule, one oxygen atom is bound to 2 hydrogens, H2O. Everyone's heard this. Everyone knows this. I hope you can see it. It's a picture of it right there, and that's what it is. And that, by the way, that angle between the 2 hydrogen atoms is critical. It's absolutely critical. If it was anything different than what it is, which is about between 104 and 106 degrees, of distance between the 2 of them, life would not exist. The chemical formula for a molecule corresponds to its atomic composition. When there are 2 or more atoms of the same element in a molecule, this number is written on the right side of the element's symbol. Many compounds are not pure. Actually, pure compounds are really kind of rare. Wine, which is not a pure compound, consists of molecules of water, sugar, alcohol, probably nitrates or nitrites, and others. Some molecules contain very few atoms, such as a water molecule, while other molecules, such as the proteins, particularly the proteins that make up you, contain hundreds of thousands. I'm going to show you this. I hope. I'm going to come around the other side here so you can see it. Your body assembles these. And if you look at it, once again, have a look at it. Every one of them has to be exactly where it's supposed to be, or that protein will not work. In which case, you have a problem. I find that amazing. Actually, this is a protein called xylanase. That is any word that ends in ace is an enzyme. I don't know if you know what enzymes are. Enzymes are something that make chemical reactions happen much faster than they otherwise would without being changed themselves. And believe me, that's making life simple. It gets much more complicated. It's amazing how they do what they do. I studied it. We cannot see atoms. However, using a very complex analytical procedure, we can deduce the internal geometry of the molecules of a compound with a high degree of accuracy. For example, we calculate the average distance and average angle between atoms, which is critical. In biochemistry, it's vital. This information is very important to chemists because the properties of a compound depend upon the arrangement of its molecules. For example, the atoms in water molecules are not arranged in a straight line, about 104 degrees. If were it not for this angle, water molecules were linear. If the two hydrogens were attached this way with the oxygen in the middle, the water would evaporate at room temperature instead of 212 degrees. In other words, without this angle, we would not be here today. I hope you find that interesting. Isn't that amazing? A full discussion of how chemical bonds would exceed the objective of our discussion, and it's really not needed. It's just you need to know what, the generalities, if you will. The important point regarding our subject is the almost magical power of these chemical bonds in holding atoms together. They have a dramatic effect on the elements, transforming them in ways that can make them unrecognizable. The elements can easily change textures, color, odor, and so on, acquire totally new properties. The various facets that each element of the periodic table exhibits by virtue of these bonds are astonishing. For example, nitrogen. You're surrounded by it. The air is almost 80% nitrogen. And it's N2. There are two nitrogen atoms for every nitrogen molecule. The air we breathe contains 21% oxygen. Almost all the rest is nitrogen, 80%. So nitrogen, in other words, we breathe oxygen diluted by nitrogen. Sums it up. Nitrogen gas is completely colorless, odorless, and inoffensive, and very stable. Its stability is a reason why it's inoffensive to us, and we can breathe it in and breathe it out. But if its concentration were to increase in the atmosphere more than it is, 80%, we would suffocate. Nitrogen gas decomposes with great difficulty because the chemical bonds between the two nitrogen atoms is very strong. However, isolated nitrogen atoms are found in countless number of combinations, each very different from the other. For example, with hydrogen, nitrogen produces ammonia, a very dangerous and noxious gas, or hydrazine, which is an explosive liquid used to fuel the space shuttle. Combined with oxygen, nitrogen can produce nitrous oxide, methane gas, and or nitrogen dioxide, a brownish red corrosive and toxic gas. It's also found in the white and odorless nitrate salts, the main component of chemical fertilizers. It's also a major component of our body. It's found in all the proteins that compose our tissues, from that of the aortic valve to the nail of your little toe. The human body contains about 2.4% nitrogen, which is not a small amount if one considers that 60 to 80% of our weight is water. In fact, an adult weighing 150 pounds are about 3.5 pounds of nitrogen in you. The nitrogen in our tissues is renewed thanks to the proteins that we absorb from the foods we eat. Its source is the fertilizers that grow crops, which in turn are eaten by farm animals. In one way or another, the nitrogen and fertilizer finally arrives directly or not on our plate, in your mouth, and in you. One thing we know is it is striking that without these nitrate salts, there might not have been enough nitrogen for us to manufacture our proteins. But now for carbon. You may have heard we are carbon-based forms. We are. Carbon is very unique. It has 4 electrons in its outer shell, and it likes 8. So it will make combinations with any other element that can supply an electron, and it likes to make 4 of those bonds. So almost every carbon combination in a compound has 4 bonds. In the case of, there's one of the chemical formulas is CH4, methane gas, very explosive and stinks. Is you got 4 hydrogens combining with 1 carbon. So, or it can combine to make carbon dioxide. 1 carbon, 2 oxygens. Each of the 2 oxygens gives 2 electrons to the carbon. The carbon has its 8 in its outer shell and it's happy. Or there's carbon monoxide, where that chemical combination is very unique. And it's, carbon dioxide is lethal and it's very easily generated in a stove from incomplete combustion. And of course, carbon dioxide will kill you. How? If you breathe in carbon dioxide or carbon monoxide, it goes in your blood, and it goes in your lungs, goes in your blood, and the hemoglobin that carries the oxygen to your cells in your body, if there's carbon monoxide, they will attach instead of oxygen. So in other words, your blood system will sit there and transport carbon monoxide to all your cells instead of oxygen, and you basically suffocate. Let's see. For example, and then what's important in the case of carbons can, as I said, will combine with 4 other elements, or 4 different, or it doesn't have to be different. We indicate like CH4, it's 4 hydrogen, 4 bonds altogether. Or so it can combine with other carbons, and often does. But it's amazing. It depends upon the structure of the bonds. Because the graphite in your, many of us grew up with what they call lead pencils. It's not lead, it's graphite. And graphite is a very soft carbon. It's pure carbon. And so are diamonds. Probably the hardest substance known to man is nothing but pure carbon. Now, this is where this gets real. Maybe this will help you understand the miracle of the chemical bonding, because they're both the same. Graphite and diamonds are both the same. Made of the same stuff. Nothing but pure carbon atoms. But it's how they combine that you can end up with graphite, or you have diamonds, or in some cases something in between. And they have like it says right here, The structural difference is dramatic. Graphite is dark, opaque, brittle, and diamond, of course, is transparent, very hard. However, if a diamond was heated to 1,000 degrees for a few minutes, its atoms will become mobile enough to shift. The diamond turns to graphite and into ash. So can you burn diamonds? Yeah, you sure can. Moreover, this transformation is reversible. Under extremely high pressure, these carbon ashes may be transformed back into a diamond. So if you accidentally transform your diamonds into ash, they can be transferred back, made back into a diamond again. And I'm going to show you this picture here. The top one is a computerized image of graphite layers, and the bottom one is of a diamond. All the dots are carbon atoms. And let me see, I'm going to come around. See how it's done? This, the graphite is in layers. And this is your diamond. And I think you can see, these just kind of slide over each other. That's why graphite, and as your lead pencil, so to speak, it's kind of a slimy feel to it, or it feels like it's lubricated a little bit. That's why. And of course, diamond, that isn't the case. For example, let me look here just for a second. Yeah. Now it says chlorine is another example. It can be found. It's found in bleach, but it's also in cooking salt. Plastic can be transferred into petroleum. A tiny seed can transform into a tree. An egg could turn into an omelet or a chicken, depending upon its circumstances. In short, thanks to the astonishing property of elements to metamorphose through their chemical bonds, they reveal many facets which depends upon their bonds. Therefore, only 100 elements are enough to generate all the solids, liquids, and gases of our planet and of the universe. All the variety of the scenery, the earth, sky, plants, animals, and all the synthetic products that chemists have already succeeded in manufacturing, the list of which lengthens every day. In short, with only the elements of the periodic table, it is possible to manufacture all that is around us and all that is in us. Indeed, what are we other than a pile of chemical compounds in constant motion? That's exactly what we are. Of course, we're going to get into a lot deeper than that in a little bit. A walking chemical factory that, while consuming energy and expelling waste, is busy day and night creating and breaking down an amazing variety of chemicals. What happens inside you every second of every day is nothing short of miraculous. In fact, our organism is occupied with only one activity: the creation and breaking of chemical bonds. That's all they do. That's why I say, I hope this isn't boring, but now I hope you understand the vital importance of this, because from this point forward, when we refer to chemical bond, you'll understand you're talking about something that's life itself. It's consciousness itself, or at least of our earthly existence here. This activity transforms us. We grow taller, older, fatter. Well, at least I'm not fatter. The color of our skin and our hair changes. Sorry. The creation, breaking, and modification of these chemical bonds is called a chemical reaction, and that's the subject of our next chapter, and that's the subject of our next show. And I promise you will get more and more interesting. I really hope you're not bored. But this is so. If you don't understand this, or have an idea what we're talking about, the rest, and even more important, it's you. You got all this in you. That's like I said, that's all your body does. With chemical bond, making them, breaking them. Why? Energy. Because that's what you live on. That's what the universe is. That's all the universe really is energy. It's being transformed from one form to another. And I guarantee you it's going to get very interesting very quickly. So please like us on Facebook if you haven't already, and I hope you enjoyed this, and we will see you next week.